Qwen-VL makes a broad promise in the title of this 2023 paper. It calls itself a versatile vision language model for understanding, localization, text reading, and beyond. That word, versatile, is doing a lot of work. We need to find out how much the paper really supports. The released Qwen-VL model gives us one concrete visual example. Its answer contains the word woman, followed by 451, 379, 731, and 806. The word names the object. A parser uses the two coordinate pairs to draw a box around it. One text response is doing two jobs, saying what is there and where it is. That example turns versatile into four things we can check. We need the image to become language model input, the same model to produce both a word and box coordinates, training that teaches those behaviors, and reported tests that show how far the breath holds up. We will keep this answer in view while those four pieces connect. The first link is the image itself. Before Qwen-VL can say woman or write any coordinates, a 448 by 448 picture has to become a sequence the language model can accept. We left a 448 by 448 image waiting to become a sequence. Qwen-VL's vision encoder moves across it in 14 by 14 pixel steps. Since 448 divided by 14 is 32, we get 32 positions across and 32 down. That makes 1024 image positions. At each position, the vision transformer produces a feature vector, a row of numbers computed from the image. The count stays at 1024. The pixels have become 1024 vectors that the adapter can work with. Now, the sequence has to shrink. The adapter starts with 256 learned query vectors, arranged as a 16 by 16 grid. Each query is a trainable slot for one output vector. Each query compares itself with all 1024 image features and gathers a weighted mix of them. That operation is cross-attention, and Qwen-VL's adapter uses one such layer. Both grids carry two-dimensional position codes, so the mix can use where each feature came from in the image. Out comes a fixed sequence of 256 vectors. Each vector contains 4096 numbers, the same width Qwen uses for its text token embeddings. The paper calls these visual embeddings, and they are often called visual tokens. Qwen can now accept the image representation. Those vectors still have to sit beside the question and help produce both woman and its coordinates. Qwen first reserves 256 token places between an image start marker and an image end marker. It replaces the placeholder embeddings in those places with the 256 visual vectors we made, and the question follows in the same ordered sequence. The image and the question now sit on one line of inputs. That line enters Qwen's stack of 32 decoder layers. When the answer begins, each new position can look back at the question and all earlier visual vectors. That is ordinary causal self-attention. There is no added image cross-attention block inside the language layers. At the top of the stack, one output layer chooses the next token, a small piece of text from the same vocabulary every time. The chosen token joins the sequence, and Qwen repeats the step. That one list includes ordinary words, special markers such as box, punctuation, and coordinate digits. One detail looks odd. Our model input is 448 pixels wide, yet the answer contains 731 and 806. Qwen scales each box corner onto a common grid of integers from 0 to 999. The same coordinate range can describe boxes on images of different sizes. The same next token loop now writes the exact response we started with. Woman appears inside reference markers, then 451, 379, 731, and 806 appear inside box markers. The word and the box coordinates are one generated text sequence. An ordinary answer text copied from an image and a box coordinate string now share one interface. The request changes while one decoder predicts a text response. The architecture adds no separate OCR head or detection head. Training examples still have to teach it which response should follow each request. Stage 1 starts with plain image and text pairs. It uses about 1.4 billion cleaned pairs, with every image resized to 224 by 224. Qwen's language model stays frozen while the vision encoder and adapter learn to turn those images into inputs it can use. Stage 2 changes the setup in 3 places at once. The image size rises to 448 by 448, all 3 model parts can update, and the data switches to 76.8 million listed multitask examples. The paper does not isolate the effect of any one change. The paper splits those 76.8 million records into 7 groups covering captioning, visual questions and answers, text reading, 3 ways to connect phrases with boxes, and pure text. The answering, reading, and localization behaviors we saw earlier are directly represented in this training mix. Across all 7 groups, the training rule stays the same. The prompt is shown first. Then Qwen predicts each next token of the target text and receives an error signal from the target. Through that one objective, the shared decoder learns to write captions, answers, copied text, and box coordinates. Then stage 3 starts from Qwen-VL. It uses 350,000 instruction examples to train conversational replies, with the vision encoder frozen and the adapter and language model still learning. The resulting checkpoint is Qwen-VL-Chat. Qwen-VL was trained for this breadth. Stage 2 includes visual question answering, text reading, and grounding, and several evaluation datasets are named directly in that training mix. Scores on those benchmarks tell us how well one model handles its trained jobs through a shared interface. They tell us less about how well it transfers to benchmarks outside that mix. So next, we'll separate benchmarks with training overlap from results the paper explicitly labels zero-shot. Take text VQA first. In the paper's table, Qwen-VL scores 63.8, but text VQA also appears in its stage 2 training list, so that result goes in the training overlap tray. Science QA-ING is absent from that list, and the paper marks its 67.1 score zero-shot, meaning the model gets no worked examples before the test. That result goes in the other tray. The first shows learned task coverage. The second gives cleaner evidence of transfer. Now take the 5 text-oriented question answering tests. Each row uses its own scoring rule. So we compare models across a row, never scores down the table. A generalist uses one model across many jobs. A specialist is tuned for a narrower job. Qwen-VL leads the listed generalists on 4 rows. The specialist reference leads 4 rows too, with OCR VQA as the exception, 75.7 for Qwen-VL against 75.0 for the specialist. All 5 dataset families are also named in stage 2. This is broad trained coverage with specialists still ahead most of the time. Grounding makes the count clearer. Across all 8 RefCOCO, RefCOCO Plus, and RefCOCO splits, either Qwen-VL or Qwen-VL-Chat is the best listed generalist. Grit is the only miss, where Qwen-VL's 78.22 sits just below Unified IO's 78.61. A specialist leads all 8 RefCOCO family splits, and every one of these dataset families appears in Stage 2 training. Stage 3 then changes which checkpoint wins. On seed bench, Qwen-VL-Chat rises from 56.3 to 58.2 overall, and from 62.3 to 65.4 on image questions, while its video score falls from 39.1 to 37.8. Across the earlier tables, base Qwen-VL is higher on 5 of 7 captioning and general question answering columns, 4 of 5 text-oriented tests, and 4 of 8 grounding splits. The result is a trade-off, with gains on some instruction and zero-shot tests alongside lower scores on many captioning, question answering, text reading, and grounding measures. These tables support one precise result. Qwen-VL was a strong 2023 generalist across several trained task families. The best specialists remain higher on most direct comparisons, and the zero-shot columns do not establish the same breadth across unrestricted, unseen tasks. With that evidence in place, we can return to the full model path and resolve the title's word versatile. Going back to the answer we started with, woman and 4 coordinates. The image became 256 visual embeddings. Those embeddings entered the same token stream as the question, and the decoder wrote both the word and the coordinate text. Stage 1 aligns images with language. Then Stage 2 trains the full path on captions, questions, text reading examples, and grounding examples, all with the same next token objective. That is how the shared decoder learns to produce the localization answer. The paper's integration claim is now concrete. One system accepts image and text input, then produces captions, answers, copied text, and boxes through one output interface. The evidence keeps that word bounded. Qwen-VL was a strong 2023 generalist across several task families it had been trained to handle. The best specialists remain stronger on most direct comparisons, and the paper does not show the same breadth without direct task coverage. For Qwen-VL, versatile means one interface, many trained tasks.